Hey everyone, I'm AIRA Santos from Mapúa University, Manila, Philippines. On behalf of my colleagues, I'll be presenting our paper entitled A Mixed Integer Linear Programming for COVID-19 Related Medical Waste Reverse Logistics Network Design. So this paper is a joint research by various universities and co-written by the following authors, namely AIRA Santos, myself, and Mr. RAYAM, Dr. Yogi, and Dr. Rita, who are joining me here in the session. And other authors are Dr. MEILINDA, Dr. SATRIA, Dr. Michael, Dr. Reni, and Mr. Bobby. So this presentation is divided into four parts. The first one is the introduction, then methodology, followed by the result and analysis. And the last part will be the conclusion and recommendation. For the first part, introduction, the spread of COVID-19 pandemic has put the whole world population in grave danger and panic. Based on the recorded data last October 27, 2021 of the World Health Organization, the COVID-19 has affected 223 countries with around 245 million infections and caused 4.9 million deaths. And in the Philippines, it ranked 19th with the highest COVID-19 cases globally. So with this, the need for medical services and protective equipment increased dramatically, causing the generation rate for hazardous medical waste, or HMW, to multiply. Handling products at the end of their life cycle when they might harm the environment and humans is called reverse logistics. So to this extent, the waste management problem falls into reverse logistics network. Hence, the network for the handling infectious medical waste of COVID-19 should be adequately designed to reduce its potential harms. Mixed integer linear programming involves problems in which some of the variables are constrained to be integers, while other variables are allowed to be non-integers. In this paper, mixed integer linear programming will be used for reverse logistic network design, handling medical waste returns, and to minimize the system cost with the cost-effective allocation of waste flows and disposal rates at waste processing facilities. So with the increasing health medical waste, the model formulation should find out how the medical waste flows and should be delivered so that the reverse logistic network can achieve the minimum total cost. So the objective of this study is to apply mixed integer linear programming for a reverse logistic network design, handling medical waste returns, and to minimize the system cost with cost-effective allocation of waste flows and disposal rates at waste processing facility. And the paper will introduce the characteristic of the reverse logistic network and illustrate the application and method for the optimization problem. So this section explains the different studies and investigations related to mathematical programming and reverse logistics. For the methodology, so we use mixed integer linear programming model in our study, and the following assumptions were considered. So the first one, only one factory was identified in the area. Second, a closed loop recycling supply chain will convey all sorts of medical waste collected and processed by the treatment centers to the factory. Third, each medical facility has independent waste generation from each other. Fourth, costs of transportation and operation are known for dealing with each medical waste type. Operating cost is assumed inclusive of storing costs and managing costs of the facility for the medical waste, while fixed costs related to waste handling are assumed to be zero. And lastly, the capacity of the given factory is limitless. So the medical waste reverse logistic network design of this paper consists of three types of nodes. So the hospital nodes, the treatment facility nodes, and the factory node. The location problem of the treatment facilities is discussed involving transportation, fixed costs, and operating costs in the network. The following are the sets in this model. So H is the set of hospitals where the medical waste are generated. C for the set of possible treatment center. F is the set of possible factories. And W is the set of medical waste types. The decision variables are XHCW equals to the amount of medical waste shipped from H to C for waste W. Say FW is the amount of medical waste shipped from C to F for waste W, and the binary decision variable AC, where 1 if the treatment facility is open and 0 if otherwise. Parameters considered in this paper are as follows. For our objective function, it aims to minimize the total reverse logistic costs comprised of transportation, operational, and fixed costs of each medical facility, treatment facility, and factory. For constraint number 1, it ensures to transport the medical waste from the hospital, ensures that the amount of waste generated by the given hospital is equal to the transported medical waste from the hospital. Constraint number 2 ensures that the amount of waste shipped from the medical facility equals to the amount of waste that will be transported to the factory. Constraint number 3 shows that the amount of waste generated and shipped from the medical facility will always be less than the maximum capacity of the treatment facility. Constraint number 4 indicates that the amount of waste type W shipped from the medical facility will always be less than the treatment facility's capacity for the specific waste type. Constraint 5 shows the total number of open treatment facilities will always be less than the total number of treatment facilities. Constraint number 6 signifies the total amount of waste generated and shipped from the medical facilities will never be negative. And lastly, constraint number 7 demonstrates a binary condition where treatment facility can only either be open or closed. So for our data collection, the data of this paper is a combination of primary and secondary data. Primary data were acquired from 3 medical facilities in Metro Manila, mainly 1 hospital and 2 clinics, representing the waste generating facilities. And at the same time, secondary data were obtained by interviewing staffs who were assigned to the waste management of these medical facilities. These secondary data are those related to treatment facilities and factories. So table 1 represents the operating cost of the factory. Table 2 shows the amount of medical waste from 3 hospitals. Table 3 is the data for the transportation cost from hospital to collecting center. Table 4 is the data for the transportation cost from treatment facility to factory. And lastly, table 5 shows the operating cost and capacity of treatment facility. So the minimization equation is solved by using AMPL solver software. It is an optimization tool proposed to solve complex integer, linear, and nonlinear mathematical problems, and GOROBI optimization, which is a commercial mathematical programming solver. So the minimal cost computed after solving in the AMPL is 302,899 pesos based on the stated model and available data with the following results for the decision variables as shown in the optimal solution. So according to the results, the minimum total cost is acquired when all the treatment facilities are in operation and with the resulting waste management shown in the optimal flow. For the conclusion and recommendation, so in this paper, the reverse logistic network design for medical waste is a problem from the viewpoint of the end disposing facility, which is the factory. So a mixed integer linear programming model was introduced, minimizing the cost of operating and reverse logistic network, and solved by using AMPL IDE version 3.6.7 and GOROBI optimization to get the optimal solution. So through this model and solver, minimal possible total cost was identified through flow process of waste from the generating facility going to the treatment facility and lastly to the factory. So in the future, the model could be further enhanced by acquisition of a much broader scale of data from primary source, as this will increase the accuracy of the results as well as the entire study. So the model could potentially be mixed with other programming model and other forms of algorithms to be part of a much more complex study. So this is the end of my presentation. Thank you for listening.
Okay, thank you po for the presentation. Okay, very typical IE in the OR field. So as everyone knows, industrial engineering is a very big, like